What is up, ladies and gentlemen? This is Dirk Hamel-Wood, and in this video I will be covering Chapter 16, Section 12, Sensing the World. Background. I just want to give you guys a little information so you understand some of the things I'm talking about. Like all other IT systems, robots operate in the same four stages: input, processing, storage, and output. They use a variety of standard techniques to process and store the data, identical to any other computer. However, because robots have manual physical applications as well as move around in their environment, their input and output peripherals differ greatly from a standard computer system. Now in this video, we will mostly be discussing the input peripherals, but in my next video, we will be discussing the output. Computer vision. Now this is a concept that's a little different it's a little difficult in AI technology today. Robots don't see as you might expect. Even if a robot is attached to a video feed, they have no interpretation or understanding of what they're seeing. The only thing a robot sees is what a computer sees: a 2D, flat collection of colored pixels. One of the most difficult challenges in artificial intelligence today is computer vision, programming a computer to understand and quote-unquote see its environment. Alternative techniques. Because of the difficulty in designing a robot to actually see their surrounding environment, many designers simply deign to outfit their creations with sensors to recognize their surroundings, instead of tackling the monolithic task of for example, they may use a proximity sensor to measure the distance to nearby objects. This is commonly achieved by using an infrared sensor, which emits light and then measures the time it takes for the reflected light to return to the robot, mapping out the surrounding environment, similar to a dolphin's or a bat's echolocation, albeit using light instead of sound waves. This is, as I said, the most common of the techniques. In this picture, it's kind of a simple robot, and three sensors on the bottom, the infrared sensors, are, as well as a sonar sensor, which is also another viable alternative. Alternative techniques. Continued. Lasers are another type of light sensor also utilized by robot designers. They work in the same way that infrared sensors do, but are much more powerful. However, they are also very limited in range, and they work poorly in low visibility conditions, such as heavy cloud cover, fog, or mist. They also have difficulty registering highly reflective surfaces such as water. Radar can also be used to detect obstacles by emitting radio waves, then measuring back the reflected waves, similar to the system used by the infrared sensors. It has a longer range and is not hindered by low visibility conditions. However, it is less accurate and sometimes detects like blanks or non-existent objects which aren't actually there. In this picture on the left, we have an example of what a simple infrared sensor would look like. On the right, it's kind of like a visual depiction of how an infrared sensor works. It sends out a ray of light, and then obviously the light that hits the kind of the bend that's closer to the sensor is going to bounce back and hit the camera or the launch point first, and the other ones are going to be farther away. And it's kind of like a probing system, and it comes back and creates a picture. Well, not really a picture, but a diagram of what the surrounding environment looks like to the robot. This isn't to say that computer vision isn't used at all. It's very difficult because the software behind it means the camera has to search for patterns and shapes to decipher the true meaning. As we learned in earlier chapters, this is very hard to do. Additionally, cameras have similar limitations to the human eye. They have trouble operating at low light and during low visibility conditions, similar to lasers and infrared. However, these limitations can be overcome to some degree, especially through the use of multiple cameras, which view the situation at different angles, also similar to human eyes. This slight offset can be used to calculate the distance between objects and to give the robot a three-dimensional understanding of the surrounding environment. Pressure sensors. This is the last thing I'll be covering. It's the last major type of sensing used by robots. They are used to signal if a robot has bumped into something, which makes it useful for negotiating obstacles. Although obviously they can't detect them before they hit them, only afterwards, so in sensitive areas this may not be the best system. These pressure sensors give robots a sense of almost touch in an imitation of human skin. Are you noticing a pattern here? All this stuff is meant to replicate human sight and human touch and human movement. Neural nets are meant to replicate the human brain. For example, a robot attempting to pick up an egg needs to know how much pressure to exert. Too much, and the egg cracks. Too little, and the egg will fall and crack on the ground. This is even more important if the robot works with humans, possibly steadying elderly patients in the hospital or picking up a baby. Obviously, crushing a baby would be not good. And then this is just two examples. The Roomba that I covered in one of my earlier videos has a pressure sensor on the front that when it hits something, it can back up and then determine that there is an object there that they can't run into. And on the right is an example of what I was talking about earlier with the pressure sensors and like gripping sensitive objects, because it would be bad if every time a robot shook someone's hand it crushed their bones into pulp. So yeah. Oh, I'm sorry. Other sensors used by robots, they're less common but are also still viable, are heat sensors, which are useful for detecting living things, magnetism, pH, sound, and humidity sensors, which are all commonly used by exploration robots to gather environmental data. These are my references, and thanks for watching.